So you hear a lot about these incredible AI agents, but how are they actually built? I'm not talking about the high-level theory. I mean the real nuts and bolts, the factory floor process of manufacturing intelligence. Well, today, we're going to pull back the curtain. We're going behind the scenes to see exactly how an AI like Tool Orchestra gets made, from the raw data all the way to the finished product.
And before we jump in, I just want to mention that this whole deep dive is made for the Rooted Layers blog. They're all about AI insights that are genuinely grounded in research. So yeah, we're not just scratching the surface here, we're going deep.
Okay, so this whole thing kicks off with a really fundamental problem, and this quote just nails it. In Gen AI, data is the new code. The biggest bottleneck isn't getting more computer chips, it's the lack of verifiable trajectory data. What on earth is that? Well, think of it this way. We have endless text from the internet, but almost zero examples of an expert perfectly using a set of tools to solve a problem step by step. And that data, that's the gold dust. It is the scarcest resource in AI right now.
All right, so welcome to the AI Factory. Our tour starts right here, at the very heart of the problem. This is where we need to understand the main challenge this entire operation is built to solve. The researchers call it the ground truth bottleneck, and honestly, it's the core reason building these super capable AI agents is just so darn hard.
So what is this ground truth bottleneck? It's actually pretty simple when you break it down. If you want to teach an AI to use a set of tools perfectly, you have to show it countless examples of, well, perfect tool use. The problem is that data just doesn't exist out in the wild. I mean, when was the last time you wrote down the absolute most optimal sequence of clicks and commands to solve a problem? Right, never. So we can't find this data. We have to make it. Okay, so if we have to manufacture the data, how in the world do we do that? Let's head over to the assembly line. This is where the raw material, that perfect ground truth data, is actually created from scratch. The system is called the tool-scale synthetic pipeline, and believe me, it is one seriously clever piece of engineering.
And the way it works is just elegant. It's a two-step process. First, in what they call environment synthesis, a large language model basically dreams up a tiny, controllable digital world. We're talking thousands of virtual APIs, fake databases, the whole shebang. Then in step two, task synthesis, another LLM starts generating questions and problems inside that little world. So it might create a fake library database and then ask a question it already knows the answer to, like, hey, who checked out Moby Dick?
And this is the brilliant part. It's what they call the closed-loop advantage. Because the entire world is synthetic, the system automatically knows the correct answer to every single question it asks. It can check its own homework instantly and automatically. You don't need slow, expensive human labelers to verify anything. This closed loop is what lets them create and check millions of these perfect examples at a scale that would be totally impossible otherwise.
But, you might be wondering, just because you can make millions of examples, how do you know they're any good? That's where quality control comes in. They use this clever filter called pass at 8. Here's how it works. A really powerful teacher model, think something like GPT-4, takes each new problem and tries to solve it 8 different ways. If it can find a working solution at least once out of those 8 tries, great, the problem is kept. If it fails all 8 times, the problem gets tossed in the trash. It's a great way to weed out any tasks that are just broken or impossible to begin with.
Okay, but it's not a perfect system, and this is super important. This manufacturing process has a couple of built-in biases, or flaws. The first one is teacher bias. It's pretty straightforward. The student, which is Tool Orchestra, can never really become smarter at reasoning than its teacher, GPT-4. It's learning from GPT-4's examples, so that kind of sets a ceiling on its abilities. The second problem is triviality bias. The system finds it way easier to generate simple lookup questions than it does to create complex, multi-step reasoning problems. And that skews the whole dataset, making it favor simple tasks. So, we've manufactured the data, we've trained our agent, and the product is rolling off the assembly line. Now we're moving into the next part of the factory, the quality control department. This is where we ask the big question. How do we actually test this thing? How do we even measure if it's intelligent?
I mean, this is the million-dollar question, isn't it? After all that effort, manufacturing the data, the complex training, how do we know if the agent is actually smart? Or did it just get really good at passing the specific kind of test we trained it on?
And that leads us straight to a classic problem in AI, and really in any kind of evaluation. It's called Goodhart's law. The idea is simple but so powerful. When a measure becomes a target, it ceases to be a good measure.
The moment you start optimizing your AI to get a high score on a test, well, the test stops measuring real intelligence. It just starts measuring how good your AI is at gaming that specific test.
So to try and get around this, the team doesn't just use one test. They use a whole battery of specialized benchmarks, each designed to probe for different kinds of failure. You've got HLE, or Humanity's Last Exam, which is cool. It doesn't ask the AI to solve a super hard PhD-level question. It just asks if it knows which tool it would need to solve it. Then there's Frames, which tests its memory. Can it handle a multi-step task and remember important details while filtering out the junk? And finally, there's T-squared Bench, which tests its economic sense. Can it actually balance the cost of using a tool versus how accurate the answer needs to be?
And this all highlights a critical difference: the gap between what you could call internal and external validity. Passing a benchmark, that's like setting a new lap record on a perfect controlled racetrack. That's its peak capability. But production reliability, that's driving that same car in the real world with traffic, potholes, messy data, changing APIs, and the very real risk of the AI getting stuck in an infinite loop that costs you a fortune. These benchmarks are great at measuring the racetrack performance, but not so much the real-world chaos.
All right, let's continue our tour and head down to the engine room, the power plant of this AI factory. Because to make any of this happen, you need an absolutely insane amount of computational horsepower. And what we're about to see is that this heavy machinery, it's not just about going fast. It's actually a basic requirement just to keep the whole process stable.
Just look at that, 16 H100s. We're talking about some of the most powerful, most expensive GPUs money can buy, all wired together. I mean, the scale of this is just mind-boggling. But why they need this much power, that's where things get really interesting.
See, this isn't just about making the training finish quicker. The training method they use, reinforcement learning, is, well, it's notoriously chaotic and unstable. If you're only looking at a few examples at a time, a single lucky guess by the AI can completely throw off the whole learning process. You need all this hardware to process massive batches. We're talking hundreds of examples at once to average out all that randomness. It's the only way to get a clean signal and force this chaotic process to actually converge on a good solution. It's not a luxury, it's a mathematical necessity.
Okay, so we've seen how the data is made, how the AI is trained, how it's tested, and the incredible machinery that powers it all. For our final stop on the tour, we're heading to the showroom. After all of this, all this complexity and cost, when would you actually deploy something like Tool Orchestra? Where does it fit in? And this table does a great job of laying out the entire landscape of options. Let's walk through it. On one end, you have the monolith approach, just using a giant model like GPT-4 for everything. It's simple to set up, but the cost per use is high. Great for low-volume, high-stakes tasks. Then, way over on the other side, you have our RL-trained orchestrator. The complexity to build it is off the charts, but once it's running, the cost per use is super low, perfect for high-volume, cost-sensitive applications. And in the middle, you've got things like RAG for quick info retrieval, or even a good old-fashioned rule-based router for tasks that are stable and predictable.
So here's the bottom line. The crucial takeaway is that choosing something like Tool Orchestra is a massive strategic bet. You're trading an extreme amount of upfront complexity for huge cost savings in the long run if you have the scale. Simpler things, like a rule-based system, might give you similar low costs, but they can't adapt. And at the end of the day, if what you need is maximum reliability and you don't care as much about the cost per query, that big single model is probably still your best bet. It's all a game of trade-offs.
Which brings us to our final audit, the big question mark at the end of our factory tour. What we've seen is that the engineering to build these agents is possible. The benchmarks prove it can work, at least in a controlled lab environment. But the real question, the one that hangs over everything, is this. In the messy, chaotic real world, with APIs that change without warning and data that's never clean, will it work? That's not just a technical question. That's the billion-dollar question the entire industry is racing to answer right now.